You might initially think that the Doppler effect, there's some symmetry in it. What I mean to say is, let's see, Doppler effect for moving source. We've already addressed the Doppler effect for a moving observer, but you might think that there's symmetry for a moving source, and it kind of is reasonable, because if Newton is moving towards a monster truck, or if a monster truck is moving towards Newton, you would think that that would be the same thing. But it's not exactly symmetric, and so I'll explain why. I want you to consider, Newton is involved in some protest here, and there's this monster truck coming up, and, well, yeah, it just ran over him. Whoa, stop, monster truck! And then what's happening is the monster truck's making some sound. So if we'll study the monster truck, like at one moment, the monster truck's right here, and it's making some sound. How does this thing look? It's like really scary, like, right? And then it's making some sound, and let's say the sound is coming from right here in the middle of the engine. And the interesting thing is, as it's moving forward, it's this is the sound that the monster truck is making. It's bunching up the sound waves in front of it. And you could think of this as somebody, this is a really messy picture. You could think of this as somebody bobbing up and down in the ocean and swimming this direction. So if we were to study the wavelength back here, this wavelength is big, and this wavelength in front is small. I'm going to call this wavelength prime, because this is what Newton's going to hear before he gets run over. So we need to establish some variables for our truck and for Newton and such. So the truck is moving at a speed, the truck is moving at a speed u. And the wave is moving at a speed v. That's always going to be our wave speed. And the wave is moving not quite as slowly as the truck. Let's see, this is going to be our truck speed, or the speed of our source. So we need to try to figure out what's going on, because Newton's over here waiting to hear the sound, and he's not going to hear the same pitch as he would have otherwise. So let's figure out how far the truck moves during some amount of time. During some amount of time, the truck goes from right here to, let's say, right here, and the wave goes from right here to right here. All right, and the distance the wave goes is v times that amount of time t, and the distance that the truck goes is u times that amount of time times t. So the wave has gone further than the truck has. But the interesting thing is, if this is t, if this is the period of the wave that's being put out, of course it's not the way that I've drawn it, but these waves are getting bunched up. That's the general idea. So I want you to agree with me that this distance, this is a distance, this distance is the wavelength observed by Newton. And that's because when the first wave crest has gone this far, the second wave crest isn't emitted until the truck is here. So if the truck were stationary, this UT thing, if the truck were stationary, it'd be right here, and the wavelength would be this whole distance right here. But because the truck is moving, the truck is emitting the next pulse, the next crest in the sound, much, much closer to the source than it was when it emitted the first crest of the sound. So we have a changed wavelength of lambda prime. That's the hardest thing to understand, I think. And then we can also say how big this is. This lambda prime business, well, it's just Vt minus Ut, right? Okay, so that's just T times V minus U. Got it, all right? That's if the source is moving towards the observer. So let's do a little bit of math. We've already established that the speed of a wave, I guess it's going to be, the speed of a wave the speed of the wave is lambda prime times frequency prime, because speed is always distance times frequency. This is meters, this is per second, and that's fine. So each of these must be primed. And if oh man, everybody sees the same speed. Do you believe that? That a moving source would still cause the wave to move at the same speed, because this speed is determined by the medium. Super important to note that the speed of the wave is determined by the medium, and so it will always be a constant. So the observer sees a different frequency and the observer sees a different wavelength, but the observer says the wave is still coming at them at the same speed, because that's determined by the medium. So if we solve this sucker for frequency, because that's what I'm interested in doing, I want to see what Newton hears the truck sound like as the truck is approaching Newton. And that's going to be, well, we'll take this is V divided by lambda prime, and we know what lambda prime is. Check it out. Lambda prime is this stuff right here. It's going to be V divided by T times V minus U. Me? V minus me? What? And, oh shoot, 1 over T. 1 over T, why that's frequency. Check this out. 1 over T is frequency, so that's frequency times, let's make this in that similar form that we had before. This is going to be 1, and I'm dividing the numerator and the denominator by V, so I'm going to have 1 minus U over V. Beautiful. It's frequency divided by 1 minus U over V. So this shows us that the observed frequency, if you're standing still and the source is moving towards you, is going to be higher. Frequency increases as source moves toward you, and you maybe predicted that. Here we go. Let's see if we can see that it moves, that it gets bigger. If we're dividing by a number that's less than 1, check it out, I'm going to be subtracting positive U over V. This is a number that will be less than 1. So it's 1 minus a number less than 1, which gives us a denominator slightly less than 1. And so we are dividing the original frequency by a number less than 1, which gives us an observed frequency that's higher. So ambulance is coming towards you, and race car. You familiar with that sound? Good. Go listen to something, because that's the way it works. What if it's moving away? Well, if it's moving away, then lambda prime will be correspondingly lengthened. Over here, our lambda prime, we could call this lambda prime for moving away from you. If you were listening from over here, you'd hear a much deeper sound. And if you're listening over here for a much deeper sound, then you'd see it moving away from you, because U would be negative. So all I have to do is I have to rewrite the equation. If it's moving away, we'd have F divided by 1 plus U over V. So let me summarize these two equations on the next sheet and say a little bit about light. Frequency prime, let's see, moving source. Moving source looks like this. Frequency prime is the original frequency divided by 1 minus or plus U over V. And I can emphasize what I've got here. Minus for toward, plus for away. The interesting thing is that the universe is expanding, and the further away we look from ourselves, the more different the colors of light of stars seem to be. We know the stars are the same stars as those we have near us, but we see their colors shifted, and it's called a redshift. Redshift. And a redshift means that all of the frequencies are slightly decreased because they're shifted towards the red from the blue. And so that implies that we're getting a smaller frequency which means that we're moving away from things. And the further away we look, the faster we're moving away from things. So it would be naive, perhaps, to suppose that we're exactly in the center of the universe and that everything is getting away from us because we're really gross. But in fact, we conclude that everything is moving away from everything else. This is an astronomical observation. We could just say that everything is expanding, or maybe I could cross this out and say space itself. Space itself is expanding, and that's why everything has a redshift, and the further away we look, the greater the redshift is. Fascinating. Sound and light both obey the Doppler effect. What if I take just one more moment and tell you how the frequency changes we'll say general Doppler effect. To summarize all that we've been seeing with the Doppler effect, I can tell you that the new frequency is the old frequency times some stuff. I'm going to say 1 plus or minus the speed of the observer divided by the speed of the wave, divided by 1 minus or plus the speed of the source divided by the speed of the wave. So again, we've got the top sign is toward and bottom sign is away. What I mean is the top sign, this plus right here would be if the observer were moving towards the source, and this minus sign right here, that's the top sign, would be if the source is moving towards the observer. So which one is more dangerous? Is the one in the numerator more dangerous or the one in the denominator more dangerous? This one, I'll answer that question for you. This one is hugely more dangerous. Because guess what? It can be 0. If you divide by 0, you'll get a very, very large frequency. This frequency, in fact, can be infinite. And that's if, when is this denominator 0? That's if we're subtracting 1 from 1. That would be if the source is moving at the speed of the wave, and that, my friends, is a sonic boom. Cool. If you're going faster than the speed of the wave, you can also get a sonic boom, because whereas previously we were discussing, I'm going to leave that up there as the hugely dangerous bit, there you can see all of that. And whereas previously we were discussing a source that was moving just barely, it was stacking these waves up in front of it. What if we had it moving at the speed of sound? This is at speed of sound. I'm just going to be general. I'm saying if we're moving at the speed of the wave, then the wave fronts that we emitted a long time ago are going to all be at the same position as the thing itself. So these are all circles that are touching on the right side. But what if also we're moving faster? Check this out. Faster than speed of wave. Moving faster than the speed of wave, then the waves that we emitted back here, we've gone beyond them. So we emitted another wave there, and 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 another wave there. Oh my goodness, we've got a cone. So here, the source was here, and then it moved to here, and then it moved to here, and then it moved to here. But you notice that the source is moving outside of those waves that it's emitting. So somebody standing over here would get hit by a sonic boom, and we'll spend some time thinking about what that experience is like.